Hello, in this video we are going to see how you can simulate a UWB antenna with CPW feed in CST. So in our previous videos we have seen that what is a UWB antenna and what are the conditions if you have to categorize an antenna as the UWB, because it has some certain bandwidth criteria, like it has to resonate from 3.1 to 10.6 gigahertz for an antenna has to be for the UWB applications. And in our previous video about CPW, we also have seen that for a CPW, the feed and the ground plane, this is the feed and the ground plane are on the same plane. And the main characteristics of CPW is it doesn't have like the cutoff frequency like microstrips transmission line. So it is very usable for the wideband applications. So this is the structure I'm going to use. Okay, so I'm going to use a circular monopole, and for designing the dimension I'm using this calculator. So I'm using the resonance frequency of 3.5. So this will be our first resonance in our UWB resonances. So I'm using the frequency 3.5, and this is the radius. Based on that calculation, I'm using this calculator. I'll put the link in description. So that is the radius of the circular patch, and these are the ground plane. So we have to put some gap in between the circular patch and the ground plane. So I'm choosing a gap of 1 mm. And this is the dimension of the CPW 1.6 and zero point 0.7 mm. This will be giving us around 71 ohm impedance. Why I'm using this impedance is as I'm using an edge feeding for this structure, the impedance at this point will be very high. That's why I'm using this feed dimension. So we have a simulation video in our channel if you have to more familiarize about these type of fields. So let's see how we can do the simulation in CST. So you can also watch this video about the CPW feed to get an idea about how the port dimension has to be selected. So let's go. Let's start. I'm using the new template antennas, then planar. So here you can use time domain or frequency domain, but we will be using the time domain as it is wideband. So go for wideband. And I'm going to use the frequencies from 2 to 12, because for the UWB the resonant frequency is from 3.1 to 10.6. So you can use this frequency. You can either increase the frequency range also. Okay, so maybe I will save this file and start. Okay, so let's start with the dielectric. So this is my dielectric, and I'm going to use the parameter DL and DW for okay, so X is along this direction, so this is along the width, so I'm going to use DW along the X and DL along the Y. Okay, so it has a thickness of 0.8, and I'm going to use the FR4 substrate. So let's FR4 lossy substrate. So we have the dielectric having these dimensions. Okay, so my DW is around 35 mm and DL is 45. Okay, and H is 0.8. That is the dielectric thickness. So we have the dielectric. So now we are going to use the ground planes. So now we have drawn the dielectric, and then we can draw this ground planes. Okay, so let's start with the ground plane. So the ground plane. So the ground plane has to start from minus dw by 2 to that width. So I'm going to use minus dw by 2 to minus dw by 2 plus that width, which is wg, and along y minimum this is minus dl by 2 to minus dl by 2, oh sorry, minus dl by 2 plus LG, and it is on the top of the dielectric, and I'm going to give a thickness of 0.035 and it is metal. So let's preview that. WG is 16, LG is 16. So this 16 WG and LG, WG is based on the factors that we have to accommodate these feed and the gap. So that's why WG is selected as 16. Okay, then we have this ground plane. So we have to draw the ground plane again at this point. So maybe we can mirror it. Okay, use the transform, mirror. Then we have to copy here. Okay, valid normal direction. So we have to also not so we have to X, right, not shape center 0 0 0. So we have to mirror along the X and the center should be this coordinate. So we have the mirrored ground plane. So we have two ground planes now. Maybe you can add it. So click on it and shift plus and then select the other. Then it will be added together. So my next aim is I have to draw the feed line. So let's draw that. So this is my feed. So it has to be along the X, that is the feed width by 2 to feed width by 2, and it has to start from minus dl by 2 to minus dl by 2, oh, sorry, minus dl by 2. So it has to go all the way from here to here, then 1 mm gap, then the radius of the patch. So it has to be dl by 2. That means it has to be from minus dl by 2 plus lg plus 1 mm and plus radius of the patch. So that should be our dimension. So lg plus radius, we can give it as r, and then, oh sorry, there is one more 1 mm. Okay, feed width is 1.6. Okay, radius we have selected as 11.8. Okay, let's preview. Oh, so this is on the top of the patch. Okay, so now we have the feed. Okay, so next is we have to draw the cylinder. Sorry, that circle, that is our patch. Okay, so the outer radius, x center is 0, y center is, we have to select this point as the center, so that has to be minus dl by 2 plus lg plus 1 plus r. Okay, so this should be the y center, and z minimum, that is the thickness of the dielectric, as it has to be on the top. Okay, let's preview that. Okay, so we have the patch and the feed. So maybe you can add the patch to the feed. So we have the structure here now. So now our next step is to assign the port. To assign the port, maybe you can select these points and go for the waveguide port. So where is it? Port, new waveguide port. Okay. And So this has to be based on the dimension plus 3 and it has to be 2.5. Okay, so we have the port and okay, maybe you can assign some field monitors like E field maybe for 3. You can use the sub volume structure bounding works. Then the calculation domain can be reduced. Okay, apply. Yes. Some other frequencies also 7 and then maybe 10 also. So similar thing can be done for the magnetic field also. And the next thing is far field. For far field maybe we can use the transient broadband and if you really need good results you can go to the global properties and increase these mesh settings. Okay. Then okay, I started the simulations and I had to make some adjustments in my mesh settings as it is the learner's license. So this is my simulated S parameter and here you can see that how the resonance is formed from 2.5 to more than 11 gigahertz. So this is having a UWB for performance. And if you go for the far field, one of the importance of UWBs, it has to be have a omnidirectional pattern. So maybe we can check the frequencies 3. So you can see that the pattern is omnidirectional. So maybe at different frequencies, it may be similar to the omnidirectional pattern. So at some frequencies, it may be not that much like omnidirectional. You can see that as the frequency is increasing, it is like not giving us the omnidirectional pattern. Okay, then so at lower frequencies it is giving us a good response of omnidirectional pattern. So maybe you can check the electric field and magnetic field and surface current. So here you can see that how the surface current variation is happening at low frequencies, at higher frequencies. Maybe you may have to, and at higher frequencies. So at high frequencies you can see that the excitation is happening at the ends, and at lower frequencies you can see that the excitation is happening at the midpoint. So this is one of the characteristics of UWB. So the higher band is obtained due to these couplings and these type of resonance in the patch antennas. I hope you get some idea about how you can simulate a UWB in CST and how you can analyze the results. Thank you.